for the lenses and mirrors. I think that would be useful. So let's do that first. And then I'll also address one of the free response as we get into that. So it is very important that you know what types of images are formed by what types of lenses and mirrors in the different scenarios. And as you know, for the lenses, there are 4 different scenarios, and for the mirrors, there are 4 different scenarios, and they're really similar. So let's just recap that. So I'll do the mirrors on the left and the lenses on the right. The mirrors, let's first do concave. And remember, concave are a converging device. And since concave mirrors are converging, they're similar to convex lenses because they are also converging. Remember, convex and concave refer to the shape. Converging and diverging refer to what they do to the light. Okay? So concave mirrors have 3 scenarios. There's the mirror, there's the focal point. I can be outside the focal point, I can be at the focal point, or I can be inside the focal point. And in those cases, the image is here, is real and inverted. By the way, this one, I've already said this in class, so it's not a secret, but I just want to make it clear that this is one of the easier ray diagrams, not on the exam. I think it's the easiest one, and I've given you a more difficult one. I'll show you, I'll narrow it down for you a bit, okay? For this one, the second one, when it's at the focal point, there's no image at all. In fact, if you try calculating it, you find that Q is equal to infinity. By the way, up here, for the first one, Q here is what, positive or negative? Positive, because it's real, it has a positive Q, and because it's inverted, it has a negative M. Real means positive Q, inverted means negative M. And here so no image there, also not on the exam. When I say not on the exam, it means that not on the ray tracing diagram that you're going to have to do on the free response. Same for this one. I mean, you will probably have a scenario like this maybe in the multiple choice. That's not what I'm saying. As I'm saying, it's not the ray tracing on the exam. Likewise, not this other one either. So that only gives you 2 options for the mirrors. The third one is where I have inside the focal point, and in that case, I have a virtual image, I have an upright image, and I have a bigger image. Let's remember what those words mean for the variables. If it's virtual, that's negative Q. If it's upright, that's positive M. And if it's bigger, that means M is bigger than 1. Okay? And then the third one, or the fourth one rather, is I can have a convex mirror. That looks like this, where the focal point is back there. My object is here, and my image is here. That is a virtual, upright, smaller image. Okay? I'll draw the ray diagrams for both of those just to refresh your memory, since I just told you that one of these 2, or one of the 4 rather, will be on the exam. Virtual means negative Q, upright means positive M, and smaller means that M is less than 1, or really the magnitude of M is less than 1. So it's between, greater than 0, but less than, or more than, less than 0, but greater than negative 1. Okay, less than 1, but negative. Okay, those are the mirrors. The lenses are really, really similar. So for the lenses, the convex or the converging devices, 3 scenarios there, 2 focal points. I can be outside the focal point, at the focal point, or inside the focal point. Here, if I'm outside the focal point, that is a real inverted image, positive Q, negative M. It can be bigger or smaller or the same size. It sort of depends where the object is. Here there's no image. That means that Q is equal to infinity, just like on the other side. And then here, just like before, it's going to be a bigger image, bigger, virtual, and upright. So M is bigger than 1, Q is negative, and M is positive. Virtual images are always upright. That's the bet. Okay? And then for the last one, it's going to be a concave lens. Looks like this. Remember, it caves in. That is a diverging device. This is diverging. Likewise over here, diverging. Here's my object. Doesn't matter if it's at the focal point, in the focal point, outside the focal point, doesn't matter. It's always going to make the same image. And that image will be right here. It is a virtual, upright, smaller image. Right, just like over there on the left. Negative Q, positive M, M less than 1. Okay? Likewise, not on the exam, or not on the free response. Not on the exam, not on the free response. Okay, that means for your free response, you really just need to know these 4. And you only need to know 2 rays. So I'll just make sure that you can draw 2 rays and locate the image for those 4 scenarios. You want to go through those very quick? Is that useful for y'all? Okay, let's just go through them. I'll pull out my notes, just make sure I get these right. You know, some of the rays are easier to draw than others, so I would recommend that you learn those easier rays and just be prepared to do that. Do the mirrors first. All right, so for the concave mirror, when I'm inside the focal point, there's my object. The image, or the first ray, I can draw parallel to the axis and then through the focal point. Oh, that was a little crooked. Try to do that again. You can use a straight edge. Your equation sheet will be a separate sheet of paper, so you can use your equation sheet as a straight edge. The second one is going to be, well, there are a couple you can do. You can do through the focal point. So I could do a ray that is through the focal point. But remember, the ray goes such that if you were to trace it back, it's like it's originating from the focal point. You could do that one. I think that one's actually kind of difficult to do. So it might be that you decide you don't want to do that one. Instead, you might instead want to do the ray that just goes to the center of the mirror. That one's pretty easy to remember. If it goes to the center of the mirror, then it just follows the law of reflection. That would be enough rays to get you to where the image is, that your image is going to look like that. Oh, wait, no, I'm sorry. No, I did that wrong. Hold on. What did I do wrong? I think I just didn't draw it right. Parallel to the axis. I just didn't draw it right, yeah. So the ray actually goes like that. You just want it so that these 2 angles are the same. Now the 2 rays go backwards like that. And that means that my image is going to be right there. I just didn't draw it very well. I need to be better, careful with my straight edge. Okay? You can go back in the notes technique. There is one that goes through the center of curvature. I'm going to take this away just so it gets messy. There is one that goes through the center of curvature. So the center of curvature would be right here. That ray would originate from the center of curvature, go up to the mirror, and then come back on itself. It's just, I haven't been real careful in drawing my rays, that's why they're not coming out right. Yo, is it clear? Do you understand what I'm saying? Or am I confusing you even more? Am I confusing you even more? No, you good? Okay. Who has that? Okay? That's the one. It goes through the center of curvature and then goes back on itself. Okay? And so you would trace those rays back and find where they cross, and that would be the image right there. Okay? Then also, there's the convex mirror. The convex mirror is where I have an object right there. I could have a ray that goes parallel to the axis, like that, and then it's going to go through the focal point, such that if you were to trace it back, it would go through the focal point. This is a diverging mirror, so it's going to cause the rays to diverge. And then second, I could draw the ray that just goes to the center of the mirror, and then it follows the law of reflection, like that. And then if I wanted to know where the rays crossed, I would trace them back, trace this ray back. This would be that way. And then my image is going to be right here, where those two virtual rays cross. Those are probably the easiest rays to do for those. The one that goes to the center of the mirror and the one that goes parallel to the axis and then through the focal point. For the lenses, I have a convex lens where my object is inside the focal point. Probably the easiest one to do is to have one that just goes parallel to the axis and then through the focal point. So a ray that goes parallel to the axis and then it goes through the focal point. And then you could also do a ray that just goes through the center of the lens, like that. Okay, that's sort of like the one that we did that was through that goes right here. Then you can trace those rays back, and then where they cross is where the image is. So the image would be right there. And then finally, for the concave lens, this one might be the hardest. Not that that means it's on your exam, but if I have an object anywhere really, I can draw a ray that goes parallel to the axis, like that, and then through the focal point, but this is a diverging lens, so the light ray is going to go up like that, such that if you trace it back, it will go through the focal point right there. And then I could do another ray, like one that just goes, say, through the center of the lens, like that, and then that would mean that the image would be right there, where those two rays cross, the virtual ray and the virtual ray that is this ray. You can't see it, but if I trace this ray back, the virtual ray crosses right there. Those are probably the two easiest rays for those four scenarios. Okay? But look back at your notes. You might disagree. There might be some that you remember better. Okay? That's your free response. One of your free responses. One of those four. So clear on that? Questions? I see some confused looks on faces. Yeah. Yeah, let me redraw that one. I just didn't draw it very well. But it is true. If you go through the center of curvature, it just goes back on itself. It just follows the law of reflection. So if I have an object that is inside of the focal point, I can draw a ray that goes through the center of curvature. This is the focal point. This is the center of curvature. I imagine a ray that originates at the center of curvature, goes up like that, and then it reflects back on itself and goes back in that direction. So it originates at the center of curvature, goes up to the mirror, and then reflects back on itself. And then I can also draw a ray that goes to the center of the mirror, right there, and then follows the law of reflection. That is that these two angles have to be equal to one another. Now notice that these two rays are diverging from one another. So to determine where the image is, I have to trace them back. Those are my virtual rays. And so that image is going to be back here. All right, that's the concave mirror. When you're up really close to it, it makes it look really big. Okay? Yeah, this is a concave, that's a convex. That's a convex lens, that's a concave lens.
Can we do from this previous form the two rays of concave?
The number, question number. Okay, yeah. Where it's a concave lens. I don't know if I have an example with a concave lens, do I? You mean a convex mirror? Well, like this one is so concave mirrors and convex lenses are similar. They're both converging devices. So when you say a concave lens, I think they're converging device, diverging device. So it'd be a concave lens and a convex mirror. This one is a convex mirror. I can tell because the image is smaller. Is that this one? 20. Okay, let's take a look. This is a mirror. No, this is a convex. All right, a concave mirror. This is a concave mirror. You want to do this one? Okay, the reason I know that it's a concave mirror, how do I know, y'all? It's bigger, right. Hey guys, Kyla. I appreciate you. You're not bothering me, but you might be bothering the people around you. So I have an image that's bigger, and then the object. So that way I know then that it's this kind of scenario where I have an object that's inside the focal point. That means that the image is bigger, it's upright, and it's going to be virtual too. So I know that the type of mirror that it is a concave mirror. Okay? And then for the second part, I need to find the image distance. That's where we're solving that system of equations. Yours is going to be very similar to this. So you'll need to first determine the type of mirror, or lens, could be a lens, and then find the image distance. You want to do that part too? Yeah. So I would first find the focal length. The focal length, because it's concave, is positive, and it's going to be half the center of curvature. It's 10 centimeters. And then the magnification is going to be 6 divided by 3. It's also positive because it's an upright image, and so it's positive 2. Now in this case, I was given the number, I calculated the number, 20 divided by 2 and 6 divided by 3. But the sign of those numbers I intuited because I know what type of image is formed by this mirror. Okay? So I know that it's concave mirror, so it's positive, and I'm told that it's upright, so I know the magnification is positive. Then you want to solve for Q. So I set it up like this. I first say that M, which is positive 2, is equal to negative Q over P. And then I say 1 over F, that's 1 over 10, is equal to 1 over Q plus 1 over P. Everybody does algebra differently, but I find laying it out like this is probably easiest for you. It just allows you to keep track of all your variables. I like to cross multiply the first one, and so I get that Q is equal to negative 2P. Doing that just allows it to be not a fraction, so you're not dealing with fractions when you do the next part. I take this, the negative 2P, and I plug it in here for Q. I substitute it. It's solving it by substitution. Then I say 1 over 10 is negative 1 over 2P. The negative came from right here. I just brought it up into the numerator. Plus 1 over P. Then I have to find a common denominator. What's the common denominator for that right-hand side of the equation? Not 2, but 2P, right? Because I have 2P here. I can make that 2P by multiplying both the top and the bottom by 2. And if I do that, my equation now becomes 1 over 10 equals negative 1 over 2P plus 2 over 2P. That's the same equation. I just found a common denominator, and I made that second part to have the same denominator as the first part, the negative 1 over 2P. So that's 1 over 10 is equal to 1 over 2P. Yeah, that's right. And then 2P, solve that, 10 is equal to 2P, P is equal to 5. Okay, once I know P, then it's really easy to find Q, because I just say P and put it up here, So I say Q is equal to -2 times 5 or -10 centimeters. So that's Q, but I also want to know, is it to the right or the left of the mirror? Well, since Q is negative, that tells me that it's to the right. But I knew it's to the right of the mirror anyway. Did I lose my microphone? Huh? Yeah? Okay. Is that clear? Yeah. Yours will be very similar to that. It could be a it could be a lens or a mirror, either one. Alrighty? Alright, I think I've already done the raise. Your other two free response will be like these. I think this one, yeah, you're going to have a 2-lens system. I think we're okay on these. We okay on these? I can do it if you want. I think we're okay. It's really just like a 1-lens system. You just do it how many times? Twice, yeah. And then don't forget to take the product of your magnification, the 2 magnifications, because I asked what is the total magnification. You want to do number 3? Yeah, let's do it. We haven't done them a whole lot, so let's just do it. The first part, to know the slit spacing, I give you this value, and so you need that to find the slit spacing. There are 10,000 lines per centimeter. That means that the slit spacing is 1 over 10,000. That's going to be centimeters per line, or I can just say centimeters. That per line doesn't really mean anything. Oh, I don't have my calculator. Oh, shoot, I'm going to need it. Y'all, give me just a moment. How fast can I get back here? Oh, that's just like mine. Sure. Make sure to use radians with trig. Bro, I had that same note on my calculator when I was in college. Because I don't know how many exams I took where I missed questions because my calculator was in degree mode when it needed to be in radian mode when I would go into my math classes. All right, so that's 1 times 10 to the minus 4 centimeters. It will be in centimeters or millimeters, so make sure you can convert. So that's 1 times 10 to the minus 6 meters. I moved 2 places for centimeters, 3 places for millimeters. If you don't know how to convert that, make sure you know how to convert it. Every question has some sort of conversion in it. And then for the second one, for part B, that one's pretty easy. For the second one, I want to know the distance from the central maximum to the second bright spot. That second bright spot tells me that m is equal to 2. Lambda, the wavelength, is 400 times 10 to the minus 9 meters. I need to convert that to meters. Nano is minus 9. Your wavelength will be in nanometers, as always. And then L, the length to the screen, or the distance to the screen, is 2 meters. And then we have D. So 2 steps. I say that D sine theta equals m lambda. So I'm looking for theta here, inverse sine of m lambda over D of 2. Lambda is 400 times 10 to the minus 9 divided by D, which is 1 times 10 to the minus 6. Check my mode. I'm in degree mode. Look at that. Yeah. The inverse sine, be careful with your order of operations if you don't have the, especially if you don't have the EE button. Oh no. Yours is different from mine, Dawson. How do I get down? Oh, there we go. Okay. Does somebody get an angle on that? I'm sorry. What is it? 53. So that angle theta is 53 degrees. And then once I find that, I can find y is equal to L tan theta which is going to be 2 meters times sine of 53. That's going to be 2 times sine 53. Oh yes, thank you, tan. I get 2.6 meters. Okay, that's the difference between the 0th order and the 2nd order. Yours will be just like that, just different numbers, nothing wonky about it, there will be an answer. Okay? You want to get on for your response? Feel comfortable with it? How about some of the multiple choice? Any particular questions? Okay, let me just say first of all this. Those mirror and lens things come up 4, 5, 6 times. So you have to know what type of image is formed out of it so we're going to answer it correctly. In fact, sometimes, if you know that, you can answer the question maybe right away or get it down to 1 or 2 options. Melissa? 15 on 22. Okay, you'll see a question like this. If I ask you how many bright spots are on the screen, what you need to key in your mind right away is that theta is equal to what? 90 degrees. Because at 90 degrees, that's where I stop having bright spots on my screen. Because if you imagine the light coming towards the screen, when I'm at 90 degrees, it's no longer going towards the screen. All right, so I want to set that equal to 90, and I say d sine theta equals m lambda. That's 1 times 10 to the minus 6. Theta, sine 90 is 1. M is what I'm solving for. I'm going to go and divide this by lambda. 370 times 10 to the minus 9. What is that equal to? I know. I'll do it. 2.7. Thank you. So it is equal to 2.7. Now I need to interpret that to figure out how many bright spots are on the screen. So if you imagine I have these bright spots. I have the central maximum, and then there's 1, 2. And then it goes up a little bit past 2, but I don't get the 3rd order because it goes up to 2.7. So if I asked you how many orders there are, there's only the 2nd order. However, that's not what I'm asking. I'm asking how many bright spots are there. How many bright spots are on that screen? There's 5, right. There's the 1 central bright spot, and then there are 2 on either side. So if I ask you how many orders, you're going to say what? 2. If I ask you how many bright spots, you're going to say 5. Okay. Usually I ask how many bright spots are there, but I don't remember what I asked on this order of bright spots. Good question. You'll definitely see one of those tomorrow. And you're going to say theta is what? 90. That's the key, is that theta is equal to 90. But then also you need to know how to interpret this question as well. All right, what else? Yeah, Katie? Absolutely. Yeah, so d sine theta, for double slit, is equal to m times lambda. If I double, what I'm doing, I'm doubling the distance between the slits. That means that I'm doing a factor of 2 here. That means that I'm going to have, in order to keep this the same over here, yeah, because I'm asking about the distance, that means that I'm going to have a half. I'm going to decrease that by a factor of a half. If d goes up by 2, sine theta has to go down by a half. That means that y is equal to L tan theta. I can imagine then that tan theta is going to decrease by a half, so y also is going to decrease by a half. I just did something. I made an assumption. We haven't really talked about this in class, but I made an assumption, which is usually true for diffraction gratings. It's not always true, but it's usually true, or for double slit anyway, that this angle is really small. So we make what we call a small angle approximation. You might have talked about this in calculus. And the small angle approximation just means that theta is equal to sine theta is equal to tan theta. That all those things are equal when the angle is really small. Okay? So that's why I can say if sine theta goes down by a factor of a half, then tan theta also goes down by a factor of a half. And if this decreases by half, then my slit, the distance between the fringes goes also down by a factor of a half. So the answer here is C. Okay? We didn't talk about that in class, but only briefly. Is that clear? Who has? Oh, you guys, is that clear? Sorta. Let me step back through it one more time. So here, I write my equation, and then I ask what is changing. Okay, because I could say that lambda is changing, but here lambda is staying constant. I'm doubling the distance between the slits. So the distance between the slits is doubling. If I'm doing that, that means that the angle theta is going to change. The angle theta would change in order to counter that 2 by a factor of a half. And because of the small angle approximation, if this goes down by a factor of a half, this also goes down by a factor of a half. The distance between the fringes, or the bright spots, is y. And so if this goes down by half, this also goes down by half. So follow that same procedure. Write out the equation, ask yourself what's changing, write it in, and ask how the other variables change as well. Okay? There's one other on almost every exam. Let's practice. Anybody do exam tomorrow? Yeah, thank you. Yeah, well, so if lambda changed, let's try that. So I could say d sine theta equals m lambda. Let's say, remember when I did the red and the green lasers on the board, and we saw that one of them had a wider pattern? Let's say that I increase lambda by a factor of 2. That means that sine theta changes by what amount? 2 as well. And so y is equal to L tan theta. That means that this changes by a factor of 2. And so in that case, my fringes are going to move apart. That's really the only other variation that you can have, Megan, is that I can change the slits. I can change the slit spacing, or I can change the wavelength. Your order numbers are going to stay the same. Okay? Yeah. Same one. Look, these are all my students. Lillian Barber is a vet now. I think she's up on the North Shore. Anybody know Lillian? The nicest person that you will ever meet. She's like the super nice, like just the nicest, just so nice. I mean, y'all are nice. Meet Lillian. Y'all need to go meet her. She's a vet. Angel Danas, I think she's a vet too. They were both biology majors. William Robershaw, he was a chemistry major. That was a bunch of years ago. He's a researcher. Oh no, he was at MD Anderson. I think he's he's in Boston somewhere. He does like heart disease research. He does like on the theoretical side. It's really quite cool. And then y'all know Dr. Lassane, right? Y'all know Lindsay Lassane? No, she's one of our neurosurgeons in town. So she was 17 when she took this class. She just graduated early, and then she came on to Nichols. She's super. Which one? 19? You have this question, by the way, too, number 20. What's the right answer? Huh? D is right. Or no, not D. E. Although Lindsay's awesome. If y'all ever have brain trouble, I hope you don't, or spinal cord issues, go see her. She's really great. All right, 2 waves are initially in phase and have a wavelength of 2 meters. One wave travels 3 meters and the other travels 4 meters. What is seen when the 2 waves recombine? You're going to have one of these too. A couple steps. You want to first determine what is the path length difference. The 2 waves are traveling different distances, 3 meters and 4 meters. So the path length difference is 4 minus 3 is 1 meter. Doesn't matter if it's positive or negative, just what's the difference between those two. And then you ask yourself the question, what fraction of the wavelength is that path length difference? Since the wavelength is 2 meters, the path length difference is equivalent to 1/2 of a wavelength. Right? 1 is 1/2 of 2. That's correct? All right, so it's half a wavelength, and if I'm a half a wavelength out of phase, I just figure out how much it's out of phase. That gives me what kind of spot? A dark spot. That's 180 degrees out of phase is a dark spot. If it was 1 wavelength or some multiple of 1 wavelength, that would be a bright spot. And if it was anything else, it would be a gray spot, something in between. So if it was like a quarter of a wavelength, that would be a gray spot. Okay? That one's on his test too. They're all on his test. Everything. Okay? What else? 19, is this 22? Oh, I said 9. All right. Yeah, I just did that one, Jared. Is some other one you mean? Oh, 24. 19 on 24? Okay. Okay. Pretty sure you have one of these too. So here I want to know by what amount these are, by what angle are these out of phase? Y'all know what the answer is? Huh? No, 180 would look like this. If they were 180 out of phase, they would look like this. That would be 180. If they were 0 degrees out of phase, that would look like this, 0 or 360. You see the difference? Here, the peak is lining up with the trough. Here, the peak is lining up with the peak. But here I have a peak lining up with neither peak nor trough. It's in between. So what's the answer then? 90 degrees, yeah. That's a quarter wavelength offset. You're only going to see these scenarios. You'll only see 0, 90, 180, or 360. So these three are easy to spot. So if it's anything other than that, you know it's 90. It's a quarter wavelength. It's hard to draw, but it's offset by a quarter wavelength. I shifted this over 1/4 wavelength. The peak would line up with it. The peak would line up with the trough. It's just offset by a quarter wavelength. That's 90 degrees. All right, Dave? Cool. Yeah, Dave.
And 180 degrees is a half?
180 degrees is a half a wavelength. That's right. And 180 degrees is where I have destructive interference, where a peak is lined up with a trough. It's like this. That's where they go away. Okay? Anything else? Feel comfortable with the exam? All right. Let me stop this. Let me just make sure I got everybody before y'all head out the door. Y'all?